What is Bayesian statistics, or Bayesian statistics, if you prefer? Let's try to explain it through an example. So let's assume we have some kind of medical test, and for any kind of self-respecting medical test, you'll have two values provided to you. One is a false positive rate, and the other one is a false negative rate. So let's assume, for example, this is a test for COVID-19. So we would have the test being positive, given our test subject is actually healthy. So this means it would be a false positive. I hope you know this pipe notation, which means given or positive, even though the test subject is healthy. And usually you write this when you write the probability. So we can say probability of test positive given the subject is healthy. And I'll just make up a number here. So let's say we have 5% false positive rate. So this probability would be 0.05. And then we have the false negative rate as well. This would be the test is negative, even though our subject has the disease. And again, we'll just make up a probability for this. And we say, let's just say this is 2%. Now, is this really what we're interested in? Do we really want to know what's the probability that our test gives a certain result, given that whatever the subject is healthy or not healthy? Or isn't it rather the other way around? Like, wouldn't we rather want to know what's the probability, for example, that our subject has the disease, even though the test is negative, or doesn't have the disease, even though the test is positive? And this is where Bayesian statistic comes in. So we are going to turn around these probabilities now, so that even though we're given with the probability of a certain test outcome, given that the subject is in a certain state, we turn it around to saying probability of the subject being in a certain state, given that we observe this or that test outcome. The way we're going to do this is we're going to look at the possibilities, how outcomes can arise. And for our subjects, so we have two possibilities, which is either our subject is healthy or our subject has the disease. And now, again, let's just assume some numbers, put some numbers on here. Let's say the prevalence of the disease would be 1%, and this means 0.99% probability that somebody is healthy. And then starting from here, we now apply our test. So we apply our test on the healthy subjects. Here we say the test is positive. Here we say the test is negative. And then we take those numbers that I wrote there on the upper left, and we say 0.05% of positive test given the subject was healthy. And then the complementary that the test is negative in this case would be 0.95. We do the same in the case our subject has the disease. And here we said the probability, so let's put first positive, negative. The probability that the test is negative, we said is 2%. So we put those 2% here, 0.02, which means it's positive in 98% of the cases, so 0.98 here. And now we said, okay, what we want to know is, for example, the probability of our subject having the disease, even though the test is negative. So this is something that we could be interested in. So what we want to get is this path here. So we want to go to a patient or a subject that has the disease, and then further on, in this case, that we observe a negative test outcome. So what do? We say we take this here, 0.01, and multiply it here by 0.02. We're not quite finished in this case yet. So we calculated the probability of taking this path here, which would be the probability of disease and negative test outcome, which is called a joint probability. But actually, that's not what we're looking at. what we're looking for. We're looking for the probability of disease given a negative test. So what's the probability somebody has the disease among all of our negative test outcomes? So for this, we have to look at this negative test outcome and this negative test outcome. So this is going to be our denominator. So in the denominator, we also include this path here. So we divide by all possibilities of having a negative test outcome. Again, let's first take the lower path, which we already have, 0.01 times 0.02, plus the possibility of having the negative outcome, in this case, from a healthy subject, so 0.99 times 0.95. Okay, and at this point, if you want, you can actually pause the video for a little bit and just think about, not yet necessarily use a calculator, but think about your intuition. Given this false positive rate that we have here, and given this false negative rate and the prevalence of the disease in the population, what would you think? What is our probability that somebody has the disease, even though the test outcome is negative? And you can see if you have an intuition for it or not. Okay. And then what we're going to do is, of course, we are going to use the calculator and calculate this. And what we get here is 2 times 10 to the minus 4. If you didn't have that intuition, that's absolutely fine. That's why we're doing the calculations. So 2 in 10,000 will have the disease even so they have tested negative. Okay, and this, what we did here, essentially is Bayesian statistics. So we went from the probability of A given B to the probability of B given A, from the probability of a test outcome given some state of the subject to the probability of the subject being in a certain state given the test outcome. Okay, now let's abstract a little bit from this. Let's look at it in a bit more broader and maybe philosophical terms. What is this Bayesian statistics? And for this, we'll go away from this example here, and we'll do something that statisticians like to do, which is coin flipping. So first of all, if we state it in the abstract, for a non-Bayesian statistician, which generally is referred to as a frequentist statistician, variables are variable and parameters are fixed. And for the Bayesian statistician, it's exactly the other way around. For him, an observed outcome is treated as fixed and parameters are treated as variable. Even though the Bayesian statistician also knows that if we only take a sample from a population, then if we would take another sample, it could be slightly different, or even a lot different possibly. And even though he knows that actually there probably is, in many cases, some kind of fixed parameter, but nonetheless, as a Bayesian, we say, we only have this one sample, so we have to work with this sample. And even though there probably is a true parameter, we don't know this parameter, so we also express our uncertainty that we have in this parameter. So this is very abstract, so let's go to coin flipping now. And let's say we have this coin, we have some heads, we have some tails, we flip it 10 times. Let's say we observe 7 heads and 3 tails. So again, for the frequentist, he says this is one outcome of many possible outcomes. However, there is some underlying fixed parameter, and this underlying fixed parameter would be in the coin itself. And this would be the underlying probability of this coin coming up heads. This is a parameter. We don't actually know it. Even though in the sample that we have taken, we can say in the sample there was a probability of 0.7, but we don't know if we would be flipping this coin infinitely often, if it would still be 0.7 or if it would be some different value, but there is some underlying true value. So what a frequentist statistician would do, he would say, let's assume we have a certain parameter, and then we can make a distribution of our observed variables. So let's say this is heads in, let's do again 10 flips in every case. And then what we would plot here is the probability of this outcome given some underlying parameter. And then you might end up with something that looks like this. And then the frequentist statistician will, for example, ask, let's say we have here, this one would be out of our 10 flips. We observe a single head. The frequentist statistician might ask, how likely is it to observe such an extreme outcome if our assumed underlying parameter is what we assume it to be? And then he would, for example, say, okay, how likely is it that we observe such an extreme outcome or an even more extreme outcome, 0 heads, given that we assume this underlying parameter? This would then be our p-value, which is the probability of observing an outcome as extreme or more extreme as the one that we do observe. And if this p-value gets very small, then we would be in a frequentist null hypothesis testing scenario where we could say, okay, we have a very small p-value. We reject the null hypothesis that the parameter is the one that we assumed before. So this is the way frequentist statisticians reason. For Bayesians, it's different. So the Bayesian would say, okay, we have observed this experiment here, and then we want to know what is the probability that this underlying parameter has a certain value. So again, we go from this experiment here, but we would here now plot our underlying parameter theta. So what is the probability of our parameter given that we have observed the sample that we have observed, so those 7 heads out of 10 flips. And then if we would have here a parameter value of 0.7, then yeah, probably we have a pretty high probability that this is the true underlying parameter. If we say here, okay, what if the underlying parameter is 0.5? Well, that still seems pretty likely given this outcome, even so not as likely as 0.7. And then we could, for example, say, well, what is the probability that our true underlying parameter is 0.1? Well, we observed 7 heads out of 10 flips, so that's probably quite unlikely, but also not quite 0. And then we would end up with a distribution that maybe looks like this. So goes until 1 here. So what you have seen, Bayesian statistics has quite some advantages. One advantage is that the parameter is probably often what we're interested in, whereas in the frequentist case, we have this bit strange way of having to argue once around the corner. So we assume a certain parameter, we observe an outcome, and then we say, what's the probability of this outcome given this assumed parameter? The other nice thing is that in Bayesian statistics, we really say not just, okay, we accept or we reject this parameter, but we actually get an estimate and even a distribution for what we think our parameter is, and also uncertainty in our parameter estimate. Why is it nonetheless the case that Bayesian statistics is actually not used so super frequently, that in many fields the general frequentist statistics is still much more common? Well, in this case, you may already be wondering, why did I draw this distribution here like that? Where did I get that from, that it should look like this? I mean, we have observed 7 heads out of 10 flips. Wouldn't it be more appropriate to just draw something like this, to say there's a high probability of the coin parameter being close to 0.7 and 0 probability that it is anything else? Well, you can already say that's probably not so super likely. I mean, we have observed 7 heads out of 10 flips, but that doesn't mean that we think there's absolutely no chance that this can be a fair coin that has a 0.5% chance of coming up heads. And if we take it even more to the extreme, if we say we only rely on what we have seen, then somebody might also argue maybe it should look like this. So there's only probability on the sample mean, which means our parameter is exactly 0.7. It's not 0.701. It's not 0.699, but it has to be exactly 0.7. And you already see, okay, this doesn't make too much sense. So there is something reasonable of having a distribution like the one that I drew beforehand. But nonetheless, where does this come from? And so the workflow of the Bayesian statistician would be to, even before he does the experiment, say, okay, I have a certain underlying belief, a certain prior belief of what my parameter distribution should look like. And this is then modified through the experiment. So we have this prior, which is indeed called a prior. And this is an argument that's often used against Bayesian statistics because this has something subjective. This is something that you just decide on before you observe data. So in our case, how this would look like, before we do our coin flip, we say, okay, this is again our possible values of theta from 0 to 1. Here we would have the probability of theta a priori. And then we might, for example, say we believe that any outcome is equally likely. So everything we did up to now is before we even start flipping the coin. Now we're going to incorporate the results of our coin flip. So for this, we're going to say again on the x-axis different values of our parameter theta. And then we're going to plot the probability of observing a certain sample given these values of theta. So now this looks similar to what we had up here in the frequentist case, because there we said the probability of a certain number of heads given a parameter theta, which essentially is what we have here as well. So probability of a sample, so a certain number of heads given a parameter of theta. But you have to be careful that we have different things on the x-axis. And this is exactly what I told you about before. So in the case of the frequentist statistician, we say the parameter is fixed and we're plotting different possible outcomes, so different numbers of heads. Whereas now in the Bayesian case, we say our parameter is variable, but the observed outcome is fixed. So again, we're going to ask what is the probability of this outcome at different parameter values. And this is something that can be easily calculated, and we may end up with a distribution that in this case probably looks something like this. Maybe with the peak a little bit further to the right side. And from this one, we're then going on to what we're eventually interested in, which is the probability of parameter given observed sample. So, and on the x-axis again, theta. So how are we going to get this? Reminder to what we had before, probability of parameter given sample equals probability of sample given parameter times probability of parameter. Then we still have to divide by the probability of the sample, but since on the x-axis we have theta, so this doesn't depend on the sample, this essentially only becomes a normalizing constant, what we have in the denominator. And our numerator is the product of the distribution that we have here and the distribution that we have here. So this means we're going to take this product for every value of theta. So we can take it for this value, we'll end up with a point here. We'll take it for this value, we'll end up here for some lower value. Essentially, we'll get, in this case, a distribution that looks exactly like our likelihood, because we started off with a flat prior. If the prior looked differently, then this would be looking differently than the likelihood, and this is our posterior. This is the thing that we're interested in. Again, the problem was that we started off somewhere, some prior assumption before even doing the experiment, and this is something where you can get criticized for, that this is subjective, what kind of distribution you select here. Now you might say, well, why not always go for this flat prior? Then we essentially don't put any preference on any parameter. But you might ask, even in this case of the coin flipping, is this really such a good idea? Do we really want to say we have as much probability on the coin can only come up heads, or the coin can only come up tails? For every single flip, we want to put as much probability on this as that it's a fair coin. Or shouldn't we rather say, okay, most coins are, close to fair coins, somewhere near 0.5, and then we would have maybe more a distribution that looks like this for our prior. So we believe it's most likely to come to have an underlying probability of somewhere around 0.5, or maybe more extreme, even putting even more weight on 0.5 and less on those very extreme outcomes. So you see there are many cases in which a flat prior may not necessarily be very justified, and where you favor extreme outcomes by even using a flat prior. And we can even go back to our medical example for our medical test and think about it with respect to a prior. So what we had in this case, I gave you these values here. I said we have an underlying disease prevalence of 1%, and therefore this 0.99% of healthy people. And in this case, how I presented it, I think it made sense. So it was still mainly about we want to evaluate how good this test is. But in many other cases, that's actually not what you want. But in many other cases, you perform a test because you really want to know about some underlying characteristic of your population. So for example, in this case, you want to know what actually is the prevalence of a disease. And that's why you're performing the test. You may very well have those values on how good your test is, or some very good estimates on this, but you might not know how much or how many healthy versus diseased individuals you have, because this is exactly why you're performing the test. And you can still use what I presented before. However, in this case, these are not values that are somehow given, but these are prior assumptions. And in this case, you probably wouldn't say I want to have exactly 1% of disease, but some kind of distribution of the underlying probability of that someone has a disease. And again, you can see here a flat prior is probably not necessarily the best idea. So you don't want to start off with saying, okay, I assume that 50% of my subjects have COVID if it is known from other studies that maybe the prevalence in the population at the given time point is only somewhere around 1%. So you would rather start off with something that seems reasonable rather than going for this flat and completely uninformative prior. You could also think about it in a different case. You want to say, okay, we have an idea of the disease prevalence, and I'm doing this test on one specific patient, and for this specific patient, I want to know what's the probability he has the disease given this test. Maybe this patient comes in and he actually is a patient, so he presents very strong symptoms. You then probably also don't want to start with a prior that's based on the general disease prevalence in your population. So you want to say this person probably has a higher prior probability of having the disease, not just this 1%, but maybe for him something closer to 50-50. So this is one of the nice things about Bayesian statistics, that you can update your belief. So you start off, well, he's a person from this population, but he has symptoms. The probability of him having the disease, given that he has symptoms, is already different than the underlying probability in the overall population. Then you get your test outcome, and then you say, given this test outcome and that he has symptoms, we have a new probability. So this is a nice feature of Bayesian statistics. But however, what remains is that you started off somewhere from a prior, which can always be criticized for being subjective.